I do hope we can move this trial along more rapidly, counselors. We really don't have to burden the jury with hearing from every organelle in the eukaryotic galaxy. Surely the testimony is quite adequate to show how mitosis works. And no, we don't have to hear from the plant cell witnesses. I'm sure we all understand it sufficiently well. Now, Counselor Liv, at our last session, we left off with a witness for the prosecution having been sworn in. Was it Mr. Spermicide?
Yes, Your Honor. He is primary spermicide, and the defense has already stipulated that he will be accepted as an expert witness for the process of meiosis. You will recall that he comes from Martha's husband, Sam, and his testes. He has been involved with the meiosis process ever since Sam's puberty.
Very well, Mr. Spermicide. Please come back to the stand. Come on, sir, don't hang back. No need to swear you in again. Let's get on with it, Mr. Liv.
Now, sir, I believe you were explaining the cell division process that occurs in the testes. Is it different than in the skin and other parts of the body, right?
That is quite correct, Counselor. The cell division in the sex glands doesn't lead to identical cells like we typically find in mitosis. No, indeed, at least 4 sperm cells, each absolutely unique, quite special, quite.
How so, Mr. Spermaticide?
Let me remind you that all cells in the human body start with 46 chromosomes, but actually these are not really 46 completely different chromosomes. No, sir. There are 2 sets of 23 chromosomes. One set has come from Sam's mother, and the other set from his father. Put them together and you have Sam's 46 chromosomes all jumbled up in the nucleus, running the business of his cell.
But if it is the case that all the cells in Sam's body have the same set of chromosomes, how come the cells act differently? Why do skin cells act like skin and nerve cells act like nerves, and not vice versa? I should think that...
I object to this line of questioning, Your Honor. This is immaterial and irrelevant to the case.
Pause.
Overruled, Mr. Oversight. It is necessary for the prokaryote jury to understand how the cells in the colony differ from one another, even though they have the same set of instructions. You may answer the question, Mr. Oversight.
Gladly. You see, even if all cells have the same chromosomes and the same genes, now all the same genes are turned on. A muscle cell has only the genes for being a muscle working, while the skin has only skin genes working. There's all that there is to it.
That's fine, Mr. Spermaticide. Now continue with what happens when the sperm cells are formed.
Certainly. Now you'll remember when Mr. Nuclear Membrane testified. He said that during mitosis, all of the chromosomes moved up to the center of the cell in a line. All the chromosomes also line up during meiosis, but they line up in a different way. In fact, everything is different when we sex cells do it. We're the only ones in the body that go through meiosis. We have a special job to do. We have to make sperm and eggs. We're certainly not your run-of-the-mill sort of cells. All the other cells go through mitosis. They are simply making clones of themselves. We, however, out of there are making something unique. It's rather clear, isn't it, how special we are? Let me illustrate what happens when one of the sperms is found. Naturally, I brought my own set of diagrams along. They show what happens to the human cell.
You might know.
I'll have none of that nonsense in my courtroom, Mr. Oversight. The bailiff will set the diagrams up on the easel for you, Mr. Oversight.
Very well, I'll continue. Now you really have to notice this. Take a look at how the chromosomes line up during meiosis. Just look at that, won't you see? It isn't random at all. There are 46 chromosomes in a row. No, sir, there are 23 pair of chromosomes in a row. Although I can only show 2 pairs in Exhibit A, but look how Sam's chromosomes from his mama are paired with his dad's set. The numbers are together in 2s and 3s and so on. And if you look closely, you can see that each chromosome is composed of 2 chromatids. This is exactly like we saw for the skin cell demonstration.
I need a little clarification here from my poor judge's brain. Are you saying that when sperm are going to be made, the cell starts off in pretty much the same way as when a skin cell or a muscle cell is going to be made? That is, each chromosome's DNA first makes a copy of itself and the nuclear membrane disappears during interphase?
That's absolutely correct, Your Honor.
And what you're telling me I see in Exhibit B is that the chromosomes move to the center of the cell, but this time they line up with the mother's and the father's side by side. That is, I could look inside and see the number 2 chromosomes next to each other, and a little further along, I can see the 2 number 16s and so on down the line. Why? If I look close enough, I could see the chromatids. In fact, they will look like teams of our 4 chromatids.
That's it, Your Honor. You have it precisely.
And so, please explain the relevance of that arrangement to me and the jury. I can see them puzzling along with me.
Yes, indeed, but I must just digress for a moment. I need to.
I do object. Object. What is this, a biology lesson? Surely, We have listened patiently about all this coming and going long enough. We all get it. Mitosis is different than meiosis. Isn't that sufficient? Let's move the trial along. My client is different than other little gametes. We have granted that. She's on trial for her life. Why are we listening to this lecture about sperm? My client is an egg cell, for God's sake.
Sit down, Mr. Oosite. I will have no further outbursts in my courtroom, or I will cite you for contempt. Do you understand?
Yes, Your Honor, but this is extremely frustrating, and I am sure that the jury is as disturbed as I. Just look at them. My objection still stands. What is your ruling, if you please?
Mr. Oosite, your point is well made. Counselor Liv, are you going to connect this up in some way? Why are we talking about sperm instead of eggs?
The formation of sperm and eggs are essentially the same, Your Honor, but it is easier to explain if we first look at the simpler sperm formation. We will make the connection in a moment.
Very well then. Continue with your testimony, Mr. Spermicide. I will withhold my ruling for the present.
Thank you. The point I was making is that when these pairs of chromosomes lie by side, they touch at many points. That's when they sometimes swap parts. And you can see that represented too in Exhibit B. Pieces of Sam mother's chromosome number 7 can change pieces of Sam's father number 7. It's quite like a mix and match affair. You see it gives variability to chromosomes. This is called crossover by the geneticists.
Does it occur often?
One.
Oh, absolutely. In fact, in humans, every meiotic tetrad, that's what the 4 chromatids are called, there are about 10 crossovers. So by the time the crossover is finished, the individual chromatids can hardly be thought as of mothers or fathers anymore. They are hybrid of the two.
Let us now return to the main point, Mr. Spermaticide. What is the result of this peculiar arrangement of the chromosomes?
Well, just like in this mitosis, there are some threads that are formed in the cell that attach to the chromosome. There are the spindle fibers that act to pull the sets of chromatids chromosomes apart. Look at Exhibit T. See. This time, through the chromatids of the chromosomes won't be separated. Only the pairs of the mother and father chromosomes are separated.
Do you mean that that's all the mother chromosomes go one way and the fathers go another way and end up in different cells?
Oh dear me, no. Did I say that? No. Oh, I see what the trouble is. I didn't make a crucial point. The diagram might be slightly misleading. When father and mother's chromosome pairs lie together, that doesn't mean that they line up so all of the mothers are on one side and the fathers are on the other. Nothing could be further from the truth. No, they can be on either side. It is just chance that the mother's number 10 on the right side of the cell and the father's on the left. It could have just as easily been the opposite, so the end result is that it's simply a mixture. The only thing that counts is that each side gets a complete set of chromosomes.
That's this variability point again. It sounds like each cell is going to be a pretty unique collection of genes. What happens next? Complete sets of chromosomes are on each side of the cell. Does that mean the cell is going to divide?
You're correct, Mr. Liv. 2 cells are formed, each with its own collection of 23 chromosomes as represented in Exhibit D. But wait, things are not over. The chromosomes still have their chromatids. Remember them? Now the cell goes to work and pull these apart.
An excellent explanation, Mr. Spermaticide. I surmise that you are about to tell me that they now go through the same steps as mitosis. The chromosomes line up in the center of the cell, and the spindle fibers pull the chromatids apart so that...
Hold it. I object. Your Honor, I've been patient long enough. Who is the witness here, and who is the attorney? It's a cute routine that they're putting on, but come on now, this is clearly leading the witness.
I agree, Counselor Oosite. Objection sustained. Mr. Liv, please do not lead the witness. Rephrase your statements.
All right, Mr. Spermaticide, please tell us what happens next.
Well, you definitely are correct. In Exhibit E, you see the nuclear membrane again dissolving, and in Exhibit F, the chromosomes are lining up in the middle of the cell. Just like in mitosis, and it doesn't matter how to get into line as long as they do. Then the spindle fibers attach to the chromatids, and Exhibit G shows the fiber pulling them apart. This way, each side of the cell gets a complete set of instructions. And then the cells divide. That's it. Mitosis is finished. If everything is perfect, each cell at the end has one complete set of instructions. Each sperm has 23 chromosomes, and of course, there are 4 of them produced. In the first stage of meiosis, we produce 2 cells. In the second stage, each of these divide again, produce 2. That makes 4, doesn't it? After all, the really is the basic idea of meiosis, isn't it? To have a normal cell with 46 chromosomes go through duplication, and then instead of dividing only once, it divides twice. This makes 4 cells, each with a set of chromosomes, instead of dividing only once and having a cell with 2 sets of chromosomes. That's what you see in Exhibit H.
Yes, indeed.
Your witness, Counselor Oosite.
Yes, indeed.
Your witness, Counselor Oosite.
I hardly know where to begin. This explanation is so confusing that I don't wonder that the jury is baffled about what is going on here. You're telling us that meiosis leads to 4 cells, not 2 like we saw previously in mitosis, right? And you seem to be suggesting that with all this crossover and mixing of chromosomes, each sperm cell is unique. If that is so, I am correct in saying that one variation is just as normal as the next.
Well, I'm not sure. I would say that. I guess I would say that some cells are more normal than others. If it is a mutation, I would say that a cell is a suspect.
Why is that?
Because most mutations decrease the chance that sperm will survive. Most mutations are bad.
But not all, right?
Right.
Fine. Now let's get the picture of what happens in the egg. In the formation of sperm, meiosis leads to 4 cells, each with a set of chromosomes. I take it that these 4 cells are really called sperm when the process is finished. Sperm, is that right?
Absolutely, they're sperm with great rental tails and great potential. I must say, in fact, I've got some more fascinating diagrams.
No, that's quite all right. I think we've seen enough of those. Please continue.
Oh, okay. Well, in the formation of the egg, exactly the same process happens. The primate oocyte, rather like oocyte, will eventually form an egg. You will go through 2 steps of chromosome shuffling, and at the end, the 4 cells will be formed. The only real difference is that 3 of the cells will be tiny, won't be huge, rather like a pine. The tiny ones are called polar bodies, and they just disintegrate. The huge one is the egg and has all the nutrients and cytoplasm safe for itself. See for yourself how well the defendant this would need to.
Please, Mr. Spermicide, confine your remarks to the general situation and refrain from making personal asides. Now, one more question, sir. Is it true that many egg cells that develop in an older woman like Martha don't go through exactly the same steps? Lots of times there are differences.
You are definitely correct. Older men and women seem to have more mutations in it.
That will do for the moment, Mr. Spermicide. Now, tell me what were the events that have led to the special chromosome pattern that we see in the defendant, egg cell number 6624223.
As I understand, she has an extra chromosome 21. This can happen in women's eggs that is developing, especially in older women. This is a simple mistake.
Please, don't refer to it in that way. There are thousands of women that produce these eggs each year.
I object to Counselor Oocyte leading the witness. If the witness says it is a mistake, then that is what he means. He has been certified as an expert witness, Your Honor.
Objection sustained.
Please, tell us then how this situation occurs to millions of women each year.
It is simple, really. Everything is fine through the first stage of meiosis. The chromosomes take copies, they line up in the center, and the parent chromosomes separate. We now have 2 cells between 3 chromosomes or chromatids. Then the trouble starts. When the chromosomes line up again in the center, it's time for the chromatids to separate. All goes well, except the chromosome 21 doesn't always separate completely. If this happens to the eggs, I'll end up in the extra copy of 21.
It sounds like if this egg is fertilized by a normal sperm cell with its 23 chromosomes, then the baby that results will have an extra chromosome 21.
Yes, the condition is called trisomy. Leads to a baby that has Down syndrome. About 1 baby in 600 has 3 times 21, but a woman over the age of 40, 1 baby out of 50 will have Down syndrome.
This sounds pretty common to me. It's hard to imagine that one would want to